Okay, let's take a look at quiz 11. We have a Rankine cycle, and I've drawn here a Rankine cycle, a simple Rankine cycle. We have an ideal turbine and an ideal pump. So we have work of the pump and the work of the turbine. So ideal means reversible and adiabatic, so they're isentropic. So we'll find the work of our ideal turbine and the work of our ideal pump to get our network. Divide that by QH, and here we have QH here. QH coming into the boiler section. That's our high temperature energy coming in and boiling the liquid and superheating it to 900 degrees Fahrenheit. And our high pressure was 100 psi, and our low pressure was 1 psi. Let's say going into the turbine we have H. If you take that from the Moyer diagram, let me draw a little Moyer diagram schematic here. Something like that. You have a pressure line of 1 psi and a pressure line of 100 psi. If we go in at 100 psi and 900 degrees Fahrenheit, we find that the H there is approximately 1480. You drop at constant entropy, which is a vertical line on the Moyer diagram, constant entropy down to 1 psi. See, this is 100, this is 1. So down to 100 psi, down to 1 psi through the turbine at constant entropy. And the enthalpy coming out was, let's see, approximately 1050. So the work of the turbine per mass is the difference between those, or that comes out to approximately 430 BTUs per pound. BTUs per pound is the work of the turbine. Now the work of the pump, you were told it was a saturated liquid coming out of the condenser. Here's the condenser, here's the boiler. Coming out of the condenser, it was a saturated liquid, and at that point, saturated liquid at 1 psi, H was equal to 69, or let's say 69.7 BTUs per pound. And then coming out of the pump, we have the work of the pump is equal to V, which is 0.016 feet cubed per pound, times delta P, which is 100 minus 1 psi. Now you've got to multiply that times 0.185 to get it into BTUs. And so you have BTUs per pound mass comes out to approximately 0.3. So we have H2 would be, let's call this state 1 here, state 2 here. H2, H1 is 69.7, H2 would be, add the 0.3 to that and get 70. H3 was 1480. And H4 coming out of the turbine is equal to 1050. And so we can get the network is the work of the turbine minus the work of the pump. And we'll divide that by QH to get the thermal efficiency. And that comes out to, I think we said the work of the turbine was 430 minus 0.3. And the balance around the boiler superheater gives us H3 minus H2. That's state 3 coming out of the boiler. H3 minus H2 would be 1480 minus 69, or actually that's 70, minus 70 coming out at H2 would give us thermal efficiency of 0.31 or 31%. So that's the answer to question A. Question B was how much heat is input. And here we calculated just a second ago the heat input is 1480 minus 70 BTUs per pound, or 1410 BTUs per pound. Now we've got to multiply that times the mass flow, 10 pounds per second. And our QH comes out to 14,100. And I believe the closest to that was 14,000 on the multiple choice quiz. So approximately 14,000 BTUs per second is added in the process. Next, you are asked to find the irreversibility occurring in the condenser. Every real heat exchanger will have some irreversibility occurring due to the temperature difference for the heat exchange. Up here, we have for the steam is condensing at a constant temperature because it came in saturated. If you go back and look at your Moliere, you'll see coming out of the turbine you're saturated at 1 psi. So going as you condense it at 1 psi, it remains saturated the whole time, so the temperature is always 102 degrees, approximately 102. The water, on the other hand, is going from 70 to 90, so you're always hotter than the water as you transfer the heat from the condensing steam into the cooling water. Well, the first thing we have to do is an energy balance to find out how much cooling water we have. So we'll do that. M dot of the steam times delta H, which is 1050. Actually, that's minus delta H because it's cooling. Minus 69.7 is equal to M dot of the cooling water times, I'm going to use Cp of water, which is 1, times delta T of the cooling water, which is 90 minus 70, or 20 degrees Fahrenheit. And that's delta T of the cooling water. MCP delta T, and M of the steam is 10. So we solve that for M of the cooling water, and it comes out to approximately 490. So it takes 490 pounds per second of cooling water to condense the 10 pounds per second of steam. The cooling water is only changing its temperature by 20 degrees, where there's so much energy tied up in condensing the steam, so you need much less steam, or much more cooling water to condense the steam. In an actual power plant, those are like rivers of cooling water coming into those condensers. So now we can do the entropy balance. S generated equals out minus in, and out minus in for the steam would be 10 times S out minus S in. Now the delta S for a condensing fluid is the heat of condensation divided by the temperature. So it's condensing at constant temperature, so we can just take the delta H, or actually we need to be careful with the sign here. It's out minus in, so that would be 69.7 minus 1050, all divided by the temperature. It's like Q over T because Q is being taken out of it at constant temperature, so we can use that delta H over T, and that's divided by T, which we've got to be careful here and use absolute temperature, 562 Rankine, plus the out minus in for the water, which would be 490 pounds per second, times, and the delta S for a liquid would be Cp, which is 1 BTU per pound degree Rankine for liquid water, times Ln of T out over Tn. Be careful, use Rankine. That would be 550 over 530. And S generated is calculated that way. And this becomes minus 17.4. And for the water, for the cooling water, we have plus 18.1. So you'll notice S generated to be a real process, S generated for any real process must be positive, and you can see that it is because the positive delta S is slightly larger than the negative delta S. If we take that delta S and multiply it times the temperature of the surroundings, which you take to be the temperature of the incoming cooling water, which you're drawing from the surroundings, that's 530, you come out with an irreversibility of 378 approximately BTUs per second per degree Rankine. And so that's the answer to question 3, and that takes care of all the things we had to do for this quiz.